So question number 17. Right, these are the MCQs at the page number 21, right? So it says select the incorrect statement. Right, we are looking for the incorrect statement. The first one, Pauli exclusion principle excludes the possibility of the presence of a third electron in an orbital. Right? Pauli exclusion principle excludes the possibility of the presence of a third electron in an orbital. Yes, that is true. Right? The first statement, right, is true. Pauli exclusion principle excludes the possibility of the third electron in an orbital, right? So that is why when it comes to lithium, right, you need the 2s subshell. So with the lithium, you can't, with the third atom in lithium, you can't have all the 3 electrons in this one. This is wrong, right? For the lithium, you can't have the third electron like this as well. This is also wrong. Why is that? If that is to happen, both of these electrons are with the same set of 4 quantum numbers. Even with these two guys, both of these electrons are with same set of 4 quantum numbers, right? Same set of quantum numbers will appear with these two as well as these two. So we can't have 3 electrons in a one single orbital, right? So for lithium, the correct acceptable form is this. One is with only 2 electrons, and the next electron should fill to the 2s. This is the acceptable way of occupying the electrons in a lithium metal. Yes, this is all due to the Pauli's exclusion principle. It excludes the possibility of having the third electron in a single orbital. If that is to happen, 2 electrons will get the same set of 4 quantum numbers. That can't be according to Pauli's exclusion principle, right? So the statement is true. Second one, in a potassium atom, the number of electrons having quantum numbers N equals 3 and Ml equals 0 is 4, right? Let's copy the second statement. When it comes to potassium atom, so potassium means 1s2, 2s2, 2p6, 3s2, 3p6 and 4s1. This is 19th atom, potassium. So we are looking for N equals 3 and Ml equals 0, right? N equals 3. N equals 3 means, right, third energy level. Third energy level, right? Ml equals, so third energy level, you have the 3s, 3p and 3d, third energy level as subshells. Ml equals 0. So Ml equals 0 is available with L values right, actually L values greater than or equal to 0, right? So L value 0, right? L0 is a subshell, L, right? 1 is P subshell. With all the subshells, Ml0 orbital is available, right? So number of electrons with N3 and Ml0. So here you have one subshell, right? Here you have one subshell with Ml0. Sorry, only third energy level, no? Out of these, right? Here you have one subshell with Ml0. Out of three subshells of 3p6, right? Out of three subshells of 3p6, only one subshell is with Ml0. The Ml value is -1, 0, and +1 for these, for the 3p's. This is 3s and this is 3p's, right? So there also you have, out of these 6 electrons, 2r belongs to Ml equals 0. So these are the 4 electrons available with N3 and Ml0, right? With potassium you don't have the electrons, no? Right? So with N equals 3, third energy level, right? Ml value 0, you have 4 electrons. At the S subshell, the Ml value is 0. At the P subshell, you have Ml values -1, 0, and +1. Out of those, only 2 electrons are there with the Ml0. So altogether, 4 electrons are there with Ml0 with N equals 3, right? So the statement is true. So statement is true. The first two statements are true, right? Let's complete the third one. Third statement, right? Third one. The effective charge felt by a valence electron in nitrogen is greater than the effective charge felt by a valence electron in carbon. Right. Third one. Right. So what we know is, when it comes to effective charge, right? Okay. What is the trend in period? Going towards right of a period, effective charge increases, and going down a group, effective charge no change, negligible change. That is what we know about effective charge, right? So it is very clear when it comes to carbon and nitrogen, right? You have the if we are taking the P block, boron, carbon, nitrogen, oxygen, fluorine. That is how the things appear at the second row, right? When regarding carbon and nitrogen, right, effective charge of nitrogen should be greater than that of carbon, right? Is that EFF of carbon is less than of nitrogen, right? Very simple stuff, right? Going towards right of a period, effective charge increases. That is why actually the atomic radius decreases, right? So the statement is true. The effective charge felt by a valence electron in nitrogen is greater than that of carbon, right? So statement is true. Right now, let's come up with the fourth one. Statement number 4. Among the ions sodium plus, magnesium 2 plus, K plus, and calcium 2 plus, the two ions closest to each other in size are K plus and Mg2 plus. See, so you have, what are the ions? Sodium plus, magnesium 2 plus, K plus, and Ca2 plus, right? These two are isoelectronic. With 10 electrons each. These two are isoelectronic with 18 electrons each. Sodium plus means 11th atom, plus 1 means 1 electron is released, 10 electrons. Magnesium is 12th atom, 2 electrons released as it is 2 plus. Now, potassium is 19th atom, 1 electron is released as it is K plus. Calcium is 20th atom, 2 electrons are released, so 18 electrons. So isoelectronic species, right? So these two guys are with 2 electronic shells, 2 electronic shells, and these guys are with 3 electronic shells. The valence shell is 2 electronic shells, right? 2 8, 2 electronic shells. Here 2 8 8, 3 electronic shells. So the species with 3 electronic shells are always greater than the species with 2 electronic shells, right? This is about size, no? Right? Yeah, size. So species with 2 electronic shells are always smaller than the species with 3 electronic shells, right? So size, definitely these two guys are with greater size than these. Out of these, from the isoelectronic trends, we know when the charge of the cation is larger, greater with the positive nature, the size is smaller. The size is smaller. When the charge is greater with isoelectric species, when the positive charge is greater, the size is smaller. So magnesium 2 plus is with a smaller size than the sodium plus. When the positive charge of the species is greater, size is smaller with the isoelectronic series, right? When it comes to these two guys, the calcium 2 plus is smaller than that of K plus, right? So that is how the sizes vary, right? So what they're asking is, among the ions, these things, the two ions closest to each other in size are K plus and Mg2 plus. No, K plus and Mg2 plus are the ones which are not the closest to each other, the opposite with the size, right? Which are furthest away from the sizes, the Mg2 plus and the K plus. Largest and the smallest are the K plus and the Mg2 plus. Those are not the closest. The closest two guys are these two guys, or these two guys, or these two guys, right? Okay. So basically, the closest guys are these two guys, or these two guys, right? Okay. So the statement is false. Statement is false. The fourth statement is false. So the answer is that they are looking for the fourth statement. So the answer is answer number 4. Okay. Answer is answer number 4. Right now. So fifth thing is electron gain energy of carbon is negative. Electron gain energy of carbon is negative. When it comes to the fifth statement, yes, that is true. Right, that is true. Why is that? So only 3 atoms are with positive electron gains. Only 3 atoms are with positive electron gains. All the others are with negative first electron gains. Right? Only 3 atoms. What are those 3? Beryllium, magnesium, and nitrium. Only these 3 are with positive electron gains. All others are with negative electron gains, first electron gains, right? So the statement is true. The carbon coming up with a negative first electron gain, right? The thing is clear, no? Right? So for the question number 17, the answer is answer number 4. Answer number 4. Fourth statement, right now? So that's right. If you have anything to be written. right නේද? හරි. අපි යන් ඊළඟ කේස් එකට. question number 18. right? ඉතින් ළමයි අද අපිට කතා කරන්න තියෙන්නේ මේ MCQs ටික තමයි මේජර් ફોකස් එක වෙන්නේ කතා කරන්න. right? එතකොට මෙතන අපිට අර අපේ තියරි ක්ලාස් එකේදී කතා කරන්න බැරි වෙච්ච ටොපික්ස් කිහිපයක් තියෙනවා. right? තියරි ක්ලාස් එකේදී කතා කරන්න බැරි වුණා right ionic bond එක ගැන, metallic bond එක ගැන, and we were unable to discuss about the secondary interactions as well. Those are the major things right we haven't been able to discuss at our physical class, right? So we'll discuss those things as well when we are doing the questions related to those, right? ටිකත් කතා කරගෙන යන්න ඕනේ. හරිද? එතකොට මේජර් ફોකස් එක වෙන්නේ MCQs ටිකත් එක්ක ඒ ටික කවර් කරගන්න එක අද සෙෂන් එකේදී, right? හරි. කතා කරන්න යන්න ඉතින්. right? okay. So we are leading to question number 18. දැන් ලොකු වෙලාවක් දෙන්නේ නැහැ මේ ඔයාලට ලියා ගන්න. පුළුවන් නම් ස්ක්‍රීන් කැප්චර් එකක් හරි ගන්න පුළුවන් නම් ගන්න. නැත්නම් පුළුවන් විදිහට ලියා ගන්න. ඊට පස්සේ අපි රෙකෝඩින් එක කොහොමත් දාන නිසා ඒකෙන් ඊටු ටික කවර් කරගන්න පුළුවන් මාට. right? පුළුවන් මට්ටමින් අහගෙන ලියා ගන්න try එකක් දෙන්න. හරි මම හිතන questions ටික ඔයගොල්ලෝ try කරලා ඇති කියලා. right? okay. let's copy the next stuff. Question number 18 here now. Question number 18. See what it says. The number of unstable Lewis dot pair structures that can be drawn for the peroxynitric acid molecule. Peroxynitric acid. Right. The molecule is given. They are looking for the unstable Lewis structures. So they have given the structure here. Maybe they have given the structure of a stable peroxynitric acid, right? Structure is given like this. Right? They have given you a stable Lewis structure. Right? They are asking you the unstable number of unstable Lewis structures can be drawn for this atomic skeleton, this molecule. Right? That is a requirement here with the question, right? Okay, see what we can do here. So for unstable Lewis structures, there are two reasons for a Lewis structure to become unstable. For a Lewis structure to become unstable, there are two reasons. Right? There are two reasons for a Lewis structure to consider as unstable. What are the two reasons? One is the most electronegative atom of the system. The most electronegative atom of the system carrying a positive charge. The most electronegative atom of the system carrying a positive charge is one reason for your structure to become unstable. What is the other reason? The adjacently connected atoms are coming up with same sign charges, positive positive or negative negative. The story of the adjacently connected atoms. If they are with same signed charges, then your structure is unstable. Those are the two reasons for a Lewis structure to become unstable, right? So let's try to come up with such structures, right? Okay. So we definitely know, right? With the hydrogens, you can't have multiple bonds. With the hydrogens, you can't have multiple bonds. With the hydrogens, you can't have multiple bonds. But when it comes to oxygens, you can have multiple bonds. So you can have some double bond here. If you put some double bond here, if you put some double bond here, definitely these oxygens become positive. These oxygens become positive because with two bonds, the oxygens are neutral. With two bonds, the oxygens are neutral, zero charged, but with 3 bonds, the oxygens are with +1 charge. So if you are to put a double bond here, definitely these oxygens become positive. So that means some unstable structures can be drawn with some double bond here. You can have a double bond here as well. If you put some double bond here, definitely this oxygen coming up with 3 bonds. So that means definitely it's an unstable structure, oxygen carrying positive charges. So double bonds can be written here and here for unstable structures, right? That is the major focus there, right? So even even though for unstable structures you can't exceed the octets, right? You can't exceed the octets, or you can't write structures without the octets when it comes to second order nonmetals. For an acceptable Lewis structure, even those are unstable, still the octet should be fulfilled, right? Remember that, right? That is why we are not expected to coming up with double bonds here. The nitrogen is coming up with 5 bonds, right? So for unstable structures, yes, double bond can be here or here. Let's draw those two structures, right? So there could be unstable structure like this, coming up with double bond here, right? So this is positive then, right? And this is also positive then, right? So the oxygens are coming up with negative charges there. That is one way of coming up with the coming up with an unstable structure. So you can have the double bond here, right? So that this oxygen coming up with positive charge, so it is unstable, right? The structure is unstable. So nitrogen could have 4 bonds, right? So this is one way. Sorry, you can't have 5 bonds here. Yeah, like this, right? You can't have 5 number of bonds, right? Okay. So those are the 2 forms of unstable structures can be drawn for this molecule, right? Okay, clear? So answer is answer number 2. Answer is answer number 2 with 2 unstable Lewis structures, right? Ne? හරි. අපි යමු ඊළඟ වැඩේට. This is question number 18. Right? Clear, no? Let's go to the question number 19. ළමයි මම අතරම මේ ඕගොල්ලගේ වීඩියෝස් ටික දැන් අපි මේ දැන් ඕගොල්ලගේ වීඩියෝස් ටික අපි දානවනේ ගෲප් එකට. අතන මම හිතුවා ළමයි මේ WhatsApp group එකට යනද Telegram group එකට යන්න කියලා. ඒත් ඒක නිසා මේ මොකද අර ක්ලාස් එකට පස්සේ join වෙන ළමයිට නැත්තම් ආයෙත් වීඩියෝස් ටික මිස් වෙන නිසා, right? ක්ලාස් එක පස්සේ join වෙන ළමයිට ආයෙත් වීඩියෝස් ටික ආයෙත් මිස් වෙන නිසා Telegram group එකට යනකොට ලේසි ඒක මේ handle කරගන්න. මොකද පස්සේ join වුණත් වීඩියෝස් ටික set වෙනවනේ. හරි? එහෙම වැඩක් කරන්න හිතුවා. ඊට පොඩ්ඩක් මේ අපි ඒ ලින්ක් එක දාන්නම් එක හදලා. ඒකට පොඩ්ඩක් ඒකට join වෙන්න ලේසි ඒකට. right? මොකද ඕගොල්ලෝ set එක විතරයි ඉන්නේ ඉතින්. හරි? ඉතින් මේ ෆිසිකල් ක්ලාස් එක ළමයිටත් තියෙනවා. ඒකට මේ ඔක්කොම එකට join වෙන්න. ඒකට ලේසි වැඩේ නැත්තම් අර ප්‍රශ්න තමයි ඉන්නේ. නැත්තම් අර වීඩියෝස් ටික ආයිත් දාන්න වෙනවා මේ පස්සේ join වුණාට පස්සේ. ඒක ඕගොල්ලෝ දන්නවනේ. ඒතකොට ඒක ගැටලුව නිසා මේ මම හිතුවා ඒක හිම වැඩක් කරන්න. right? අපි ඒක හිම කරමු. හරි? එතකොට මේ ඔයාලට උනත් ලේසි. ඔක්කොම වීඩියෝස් ටික දැන් තියෙනවා. ඒක handle කරගන්න ලේසි වෙයි එතකොට. හරි? පොඩ්ඩක් මම හිම වැඩක් කරන්නම් මේ පොඩ්ඩක් එහෙම group එකට දාන්නම් ෆිසිකල් ක්ලාස් එක ළමයිට, right? online ළමයිටත් ඒක හිම කරමු. right? તો ලේසි. හරි. right, let's go to the question number 90. එතකොට ඔයාලට next week ඉඳන් අපි links ටික ඔක්කොම මේ Telegram group එකට දාන්න. එතකොට ඔයාලට ලේසි එතන achieve කරන්න වැඩි කරමු. හරි. හරි. අපි යමු 20th question එකට. ඒ මොකක්ද වරි ප්‍රශ්න තියෙනවා මට message එකක් දාන්න. Telegram එකට යක් කරගෙන ඉරුණ ප්‍රශ්න තියෙනවා නම් මට message එකක් දාන්න. මගේ නම එක දාන්න. ඒකට දාන්න. මට දාන්න ඕනේ. වෙනකොට දාන්න එපා. ඕන ඕන ළමයිට ප්‍රශ්නයක් තියෙනවා ඔන්ලයින් ළමයි තියෙන ඒගොල්ලන්ට ප්‍රශ්නයක් තියෙනවා මේ නම්බර් එකට දාන්න right එතකොට මම මේක solve කරන්න හරි okay chemistry problems තියෙනවා මේකට දාන්න අනිත් problems නම් ඕන එකට දාන්න කවන්නේ හරි ක්ලාස් නම් එකේ දාන්න කවන්නේ ඒගොල්ලත් ඒක වැඩි කරයි හරි right එහෙනම් අපි යමු ඊළඟට question number 19 hard shapes ගැන question එකක් තියෙනවා see what this is the shape of F3ClO F3ClO ඉන්නවා අනිත් FClO2 ඉන්නවා and FClO3 these are the guys to consider they are looking for the shapes right let's try to draw the shapes first of all right as they are not giving you any kind of skeletons we have to draw the structures with one central atom here right so when we are to draw the skeleton like that so what should be the central atom the central atom should be the least electronegative atom or the electropositive atom or the least electronegative atom should be considered as the central atom right if you are with structures with only one single central atom right so that is how we are going with right so with this structure this is the most electronegative atom oxygen is the next best electronegativity right chlorine comes next right so chlorine is the least electronegative atom out of these three types of atoms right so chlorine should be as the central atom there so Cl is there right 3 fluorines and oxygen the skeletons right for this one the skeleton is going to be Cl at the center 1 fluorine and 2 oxygens no 1 fluorine and 2 oxygens for this one fluorine at the center 1 fluorine and 3 oxygens right let's draw the complete structures now right so fluorine we are looking for the most stable structures right so as these guys are without charges it is better to have all the atoms without charges it is better to have fluorines chlorines oxygens all the atoms without charges right so when fulfilling the octets for a zero charge oxygen should have 2 bonds oxygen should have 2 bonds for zero charge when fulfilling the octets the fluorine should have only one electron fluorine should have only one bond oxygen should have only 2 bonds when fulfilling the octet for a neutral charge zero charge oxygen should have 2 bonds fluorine should have 1 bond right okay so let's come up with that for a neutral charge oxygen should have 2 bonds fluorine should have 1 bond right after handling the second row nonmetals we are looking for the central atom right so for a group 17 atom to come up as a neutral atom it should have 7 electrons 7 of its own electrons for a group 17 atom to come up as a neutral atom it should have its own 7 electrons group 17 no? So now this chlorine is it 1 2 3 4 5 only 5 electrons around it is chlorine so 6 and 7 2 as lone pairs rest should written as lone pairs this is F3ClO for this one for oxygens to come as neutral atoms oxygen should connect it with double bonds and chlorine with 1 bond so this chlorine right to be a neutral chlorine it should have 7 electrons 7 of its own electrons now you have 1 2 3 4 5 so you need to have a lone pair to become 7 like me as we are looking for the shapes right no need of considering the lone pairs of coordinates right if you need you can write like this the octets but it is not a necessary for MCQ like this right considering the lone pairs of coordinates are not needed right to concern right so that කරන්න පුළුවන් හරි for shapes no For this one, oxygen should come up with double bonds, right? So for chlorine to become neutral, it should have 7 of its own electrons. Now you have 1, 2, 3, 4, 5, 6, 7. It's 7. It's done, right? So if you need, you can put these things, but it is not necessary, right? To come up with the shapes. Only the Vesper pairs of the central atom is concerned with the shape, right? Okay. So we are looking for the shapes, no? So what is the shape of this thing? So 1, 2, 3, 4, 5. 5 Vesper pairs. 5 Vesper pairs. We have 4 sigma bonds. 4 sigma bonds. And 1 lone pair. 1 lone pair. So the shape is coming from the trigonopyramidal electron pair geometry. The shape is seesaw. Right? Seesaw. This one with 1, 2, 3, 3 sigma bonds and 1 lone pair. So coming from 4 speeds, tetrahedral electron pair geometry, it is what? The trigonopyramidal. This one. 1, 2, 3, 4. 4 sigma bonds and no lone pairs. 0 lone pairs. Right? Yes, 4 sigma bonds. So coming from the 4 pair situation, the tetrahedral electron pair geometry, and the shape is also tetrahedral as no lone pairs are there. The shape is equal to the electron pair geometry, right? So these are the shapes, right? See whether we are with such an answer. Seesaw, trigonopyramidal, and trigonopyramidal and tetrahedral. Yes, we have answer. The answer is answer number 5. Answer is answer number 5. Right now, okay, things are here now. So you can do the workings if you need. Right now, let's complete this topic now. Right now, okay, let's come up with the next one. 20th question. So do you have any questions, Lama, regarding our class or anything? Right, class again, I'm going to chat box, right? And you can raise your hands as well, right? හරි තාම ස්ටාර්ටින් සෙෂන් එක පොඩ්ඩක් ළමයි මේ වීඩියෝස් වල පොඩි පොඩි අවුල් ටිකක් තියෙනවා රයිට් අපිට මේ මන්ත් එකේ අද්දී ටික ෆික්ස් කරගන්න පුළුවන් ඒ ඔන්ලයින් ළමයිට කියන්න අර අපිට මේ පොඩි ප්‍රශ්නයකුත් වුණා අර මේ ඔන්ලයින් සෙෂන් එකේ ෆස්ට් සෙෂන් එකේ අතන හයිබ්‍රිඩ් සෙෂන් එක අපි ඩිස්කස් කරපු පාර්ට් එක නැහැ වීඩියෝ එකේ හරි දැන් රෙකෝඩින්ග්ස් වල පොඩ්ඩක් ඒක බලන්න හරිද මේ රෙකෝඩින් දැන් රෙකෝඩින් බලන්දිත් ෆිසිකල් ළමයි වුණත් මේ ඔයගොල්ලෝගේ මේ හයිබ්‍රිඩයිසේෂන් එක ඩිස්කස් කරපු ෆිසිකල් ක්ලාස් එකේ කරපු හයිබ්‍රිඩයිසේෂන් ඩිස්කස් කරපු වීඩියෝ එකේ last 15 minutes වීඩියෝ එක මම දන්නේ මොන හරි වෙලා නැහැ ප්‍රොසෙස් වෙලා නැහැ හරි ඉතින් වීඩියෝ කරන කට්ටියගේ ප්‍රශ්නයක් ඒක හරි එතකොට මේ දැන් ඒතකොට හයිබ්‍රිඩයිසේෂන් concept එක සම්බන්ධ ඒ ඔන්ලයින් ක්ලාස් ඒ කියන්නේ ඔන්ලයින් කතාවේදී ඒ කියන්නේ ඔයගොල්ලෝ ෆිසිකල් ක්ලාස් එකේ හයිබ්‍රිඩයිසේෂන් එක ඩිස්කස් කරපු එක නැහැ වීඩියෝ එකේ රයිට් එතකොට ඒ වෙනුවෙන් අර අපි මේ අපේ වෙනම අපි ඔන්ලයින් ක්ලාස් එකේ කරපු වීඩියෝ එක මම ඔයගොල්ලෝ දාන්නම් ඉතින් ඒක පැය දෙකක වීඩියෝ එකක් හයිබ්‍රිඩයිසේෂන් concept එක එක්ස්ප්ලেইন කරපු ඒක පොඩ්ඩක් බලන්න හරි පැය දෙකම බලන්න එපා අඩු ගානේ අවශ්‍ය දේවල් ටික හරි බලන්න මේ මොකද අරකේ වීඩියෝ එක වැදිලා නැහැ රයිට් පොඩි ප්‍රශ්න ටිකක් තියෙනවා තාම පටන් ගත්ත ගමන් නිසා ඕක සෙටල් වෙයි මේ මාස ඉවර වෙද්දි රයිට් පොඩි වීඩියෝ ටිකක් තියෙනවා ගිය සතියේ පොඩ්ඩක් කවුලක් තිබ්බා මේ Zoom session එකෙත් කලර්ස් වල පොඩි ප්‍රශ්නයක් තාමත් ඒක හදාගෙන යනවා රයිට් ඒකත් ෆික්ස් කරගන්න පුළුවන් next week වගේදී right හරි ඒ පොඩි ටෙක්නිකල් එරර්ස් ටික තියෙනවා right මම හිතනවා shape එක දැන්ට කරගෙන යන්න පුළුවන් වැඩේ කියලා right හරි අපි යමු එහෙනම් ඊළඟ ක්වෙස්චන් එකට මොනවා හරි එහෙම අවුලක් තියෙනවා නම් ඔයගලට ෆීල් වෙන විදිහ අවුලක් තියෙනවා පොඩ්ඩක් මෙසේජ් එකක් දාන්න නැත්නම් අපේ ක්ලාස් නම්බර් එකට දාන්න එතකොට අපි ඒ ගැන බලන්න රයිට් හරි ක්වෙස්චන් නම්බර් 19 තමයි කතා කරේ ක්වෙස්චන් නම්බර් 20 වලට යන්න රයිට් question number 20 right see the electron pair geometry surrounds central atoms of F2IO2 plus so what are the things F2IO2 plus F2IO2 plus F2BrO2 minus BrO2 minus and IBrCl3 minus IBrCl3 minus ඕන දීලා තියෙන ටක් ගාලා මේක යන ගමු right ආයෙත් අර ඉස්සල්ලා වගේ concept එක the electropositive atom most electropositive atom out of the guys are considered as a central atom other than the hydrogen right hydrogen is never going to be a central atom right other than the hydrogen right hydrogen can't form the particle bonds no other than the hydrogens right the most electropositive atom could be considered as the central atom right okay so the iodine is central atom now two fluorines two oxygens right structures in yeah so you have Br here two fluorines two oxygens no? And here Br at the center as a central atom so one I and three Cs no, no C I should be at the center sorry okay right so the positive charge so basically for a more stable atom the for a more stable structure the positive charge should appear at the electropositive atom right negative charge should appear at the electronegative atom positive charge should appear at the electropositive atom for a stable structure right so the positive charge should appear at the iodine the electropositive atom right here the negative charge should appear at the fluorine right it can't appear at the fluorine right fluorine negative දාන්න බෑ ළමයි හරි fluorine negative දාන්න විදියක් නැහැ ඉතින් ඔක්සිජන් තමයි දාන්න වෙන්නේ fluorine negative දාලා බොන්ඩ් එකකුත් දාන්න බෑ හරි බොන්ඩ් එකකුත් දාලා negative එකකුත් දාන්න බෑ fluorine හරිද fluorine octet තියාගෙන එහෙම කරන්න බෑ fluorine එකම විදිහ උච්චර තමයි ඉන්න පුළුවන් හරි හරි එහෙනම් වැඩි පොඩ්ඩක් සෙටල් කරගමු මෙතන මේ එතකොට මෙයා පොසිටිව් වෙනවා අනික් කට්ටිය ඉතින් ඔක්සිජන් නම් ඩබල් බොන්ඩ්ස් වලින් සෙට් වෙන්න ඕනේ ෆ්ලෝරින් නම් සිංගල් බොන්ඩ් වලින් සෙට් වෙන්න ඕනේ ඉතින් මේ ටික දාන්න පුළුවන් ඒ වැඩකුත් නෑ දාන්න ඕනේ වගේ කමන්නේ දාගෙන යමු so finally iodine this is not the iodine this is iodine plus iodine plus should have 6 of its own electrons this iodine plus so iodine plus should have 6 of its own electrons so let's count 1 2 3 4 5 6 6 are there so no need of applying any lone pairs to this iodine right that is done for this one right so oxygen should come up with double bonds for neutral oxygens minus oxygen should come up with a single bond oxygen bearing minus charge means only one bond is there oxygen neutral oxygen means two bonds are there right okay then let's come up with the bromine ultimately we are to consider the third row atoms right so for bromine as it is a group 17 element for bromine to consider as a neutral atom it should have its own 7 electrons its own 7 electrons to consider it as a neutral atom see what how many number of electrons there 1 2 3 4 5 only 5 electrons are still assigned to the bromine so it should have 7 electrons for it to become a neutral so the rest the two should be applied as lone pairs right okay this one right so minus so it's like this so basically this minus should appear at most electronegative atom of system that is the normal idea minus should appear at the most electronegative atom of the system. So one can draw with a minus on chlorine, right? This kind of structure. With a minus on chlorine, definitely chlorine should come up with this kind of situation. It's a minus on chlorine, right? 8 electrons should be there. For chlorine to become minus, there should be 8 electrons around chlorine, right? This is one way, right, of coming up with a minus, as minus should be there, right? So this is one way of drawing the structure, but this is not considered as the most stable structure line. For iodine to have 7 electrons for its neutral situation, 1, 2, 3, 4, 5, 6, 7. So actually this kind of structure can be drawn, but in this kind of molecule, this is not considered as a stable molecule. You get the answer anyway, right? But this is not going to be your stable molecule, right? The stable molecule is referred to as this. The stable molecule possible is referred to as this, right? Where the iodine comes up with the minus charge. Where the iodine comes up with the minus charge. I'll tell you the reason there. Why is that, right? It's very important stuff, right? So with a minus at the iodine, that is referred to as the most stable situation, right? Okay, so with a minus charge with the iodine, that means iodine should have 8 of its own electrons. Iodine with 7 electrons, it is neutral. It should have 8 of its own electrons to come up with a minus, right? So now we have applied only 1, 2, 3, 4. So 5, 6, 7, 8. Right? So this is referred to as the most stable. Not this one. This is also stable, but this is the most stable structure. Right? So this is what we need to consider for this thing, right? Okay. Let's see why is that? Why we are to refer this one as the most stable structure, not this one? Any one of you with a good reasoning? කාටද හොඳ reason එකක් තියනවද? සාමාන්‍යයෙන් කතාව මොකද්ද? If you have a minus charge, that should appear on the most electronegative atom of your system for the base structure. If you are with a positive charge, it should appear at the most electropositive atom of the system, other than the hydrogen, right? Other than the hydrogen. That is the normal thing what we refer. But this is not the most stable structure. This is the minus appearing in the iodine central atom. What is the reason? Anyone with a good reasoning? Even with this thing, we see that. Even with this thing, we see that. Right? What is the reason? Anyone? No idea. The reason is this, Naman. The reason is when drawing the Lewis structures, what are the points we follow when drawing the Lewis structures? First, draw the atomic skeleton with a central atom with more electropositive atom at the center other than the hydrogen. Right, that is done. After that, we are doing the electron count. We are doing the electron count. That is what Lewis said, right? Then we have, after drawing the skeleton, we have to count the electrons, valence electron count. All the electrons at the valence shells should be, you have to get the summation of all the valence electron count. Then have to divide by 2 pairs, electron pairs. Then we have to remove the electrons for the atomic skeleton, sigma bonds. Then we will come up with the remaining as lone pairs. Then after coming up with the number of lone pairs, what we are supposed to do? Then what we are doing is actually we are providing those lone pairs to the corner atoms, such that they fulfill their octets. First, we assign the lone pairs to the corner atoms such as they fulfill their octets. That means only 4 electronic pairs are pairs can be there at the corner atoms such that they fulfill their octets. Octet means 4 electronic pairs. You can't exceed 4 number of pairs at corner or terminal atoms. For a stable compound, the corner atoms, the terminal atoms should have octets. Right? That is the problem here. With this one, you have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 10 electrons, not the octet. Even though it is not a second row nonmetal or it is not a second row atom, yes, you can have more than octets, but the octet is the stable situation. You can have more than octet, but octet is the stable situation when it comes to terminal atoms. Terminal නම් octet තියෙන්න ඕනේ stable condition එකට. Stable condition එක නේද මේ දාන්න පුළුවන් වැඩියෙන් අවුලක් නැහැ. එහෙම unstable හරි stable structures අඳින්න පුළුවන්. But stable form එකට corner atom නම් third row උනත් octet fulfill වෙනවා නම් තමයි හොඳම. හරි. අන්න ඒකයි මේක නැතුව මේකට යන්නේ. හරිද? එතකොට minus එකක් දෙන්න බෑ ওই විදිහට මේ octet තියාගෙන. Root 70 හරි. So this is the accidental structure. Something to learn, right? හරිනේ. අනේ එහෙනම් මෙතනින් තමයි අපි උත්තර වන්නේ. So this is not the structure we are concerning, right? It's not the structure we are concerning, but this is, right? So let's come up with the electron pair geometries, no? Is that shapes of electron pair? Looking for electron pair geometry, right? So West pairs 1, 2, 3, 4 West pairs. 4 West pairs. That means tetrahedral electron pair geometry. Here 1, 2, 3, 4, 5 West pairs. That means 5 West pairs means electron pair geometry is trigonal bipyramidal. And this one with 1, 2, 3, 4, 5, 6 West pairs. That means octahedral, the electron pair geometry. Right? So the answer is answer number 5. Answer is answer number 5. හරි නේද? කීහොම තමයි වැඩේ සිද්ධ වෙන්නේ. හරිනේ? Let's complete the stuff. Right, let's come up with the next one. 21st question. These are the MCQs of last 5 years, right? अंतिम අවුරුදු පහේ නැත්නම් 2025 questions අපිට මේක include කරන්න බැරි වුණා ළමයි. Right, 2019 to 2024 ඒ අවුරුදු පහ තමයි මෙතන තියෙන්නේ. 25 එක අපි include කරලා නැහැ මෙතන, right? ඒ last 5 years MCQs ටික තමයි තියෙන්නේ. හරි. සාමාන්‍යයෙන් ළමයි first units වලින් MCQs 6ක් 5ක් වගේ set වෙනවා. 6ක් වගේ 5ක් 6ක් අතර ප්‍රමාණයක් set වෙනවා. අවුරුද්දකට, right? Let's come up with the next one. Question number 21. See, 21st question there. The shapes of IO3 plus NS3 and some things are there again. I'll quickly go through those, right? IO3 plus shapes are right? NFCl2, then F3Cl2. Sorry, H3ClO2, F4BrO minus, F4BrO minus. minus. How do I also do same? Right, okay. How? Let's draw the stuff, right? Again, I'm quickly draw the molecules. I have now discussed the theories, so I'll quickly draw the ones, right? So plus charge should appear on the iodine, not on oxygens. Oxygens are the more intermediate atoms, so oxygen should connect with two bonds there because those should count as neutrals, right? So iodine should have 6 electrons for it to be a plus charged atom. So now you have 1, 2, 3, 4, 5, 6 days now, right? Alright, no need of writing these pairs, right? Okay. So NFCl2. So the central atom should be what? The central atom should be nitrogen. The trinity atom, no? So a trinity order is known, no? Fluorine is the first one, 4.0. Second one is oxygen, 3.5. Then chlorine, 3.16 its value, right? Okay. Then nitrogen, 3.04 the value, right? So that is how this is the order, right? So nitrogen is this trinity atom out of these guys, right? So nitrogen at center, then F and 2 of Cs, right? Okay. So all that should be at the neutral situation. So group 17 should come up with one single bond for a neutral thing, right? Okay, as corners, right? Okay, so for nitrogen to be a neutral atom, it should have only 3 bonds here. It's done, right? Octet should be fulfilled. So nitrogen should have 5 electrons altogether, right? 1, 2, 3, 4, 5, right? An octet completion, right? For the nitrogen, as it's second non-metal, right? So this thing, Cl F3O. F3O2, no? Two O's are there, okay, right? So 2 oxygens, I'll put it like this. 2 oxygens and 3 of Fs. I'll put it like this, right? So oxygen should connect with 2 bonds, right? And for chlorine to be a neutral one, it should have 7 electrons, 7 of its own electrons. Let's count the stuff for chlorine. 1, 2, 3, 4, 5, 6, 7. It is done, no? So structure will be like this, right? So for this one, Br should be at the center. 4 fluorines, right, and 1 oxygen. No? Yeah, I'll put the oxygen like this with a double bond, right? 4 fluorines, right? So for yeah, you have a minus, no? So that oxygen should come up with the minus, right? You have minus, so oxygen should come up with the minus, right? So because fluorine can't have the minus, right? When fulfilling the octet with one single bond, right? Okay. So for bromine to become a neutral, it should have 7 of its own electrons, as bromine is group 17. So now you have 1, 2, 3, 4, 5. Only 5 electrons. So the other 2 should come as some lone pairs. 7 electrons, right? Okay. So this is the structure. Right now. So they are looking for shapes. Yes, shapes. So 3 West units. 3 West units. So 3 sigma bonds. Right, 3 sigma bonds and 0 lone pairs. 3 sigma bonds and 0 lone pairs. That means this is trigonal plane shape. This is 3 sigma bonds and 1 lone pair. I like it, lone pair, right? So 3 sigma bonds and 1 lone pair coming from the tetrahedral geometry. It is trigonal pyramidal shape. Here, right, you have 1, 2, 3, 4, 5 sigma bonds. 5 sigma bonds and 0 lone pairs, no lone pairs. So it is coming from the trigonal bipyramidal electron pair geometry. As no lone pairs are there, the shape is also trigonal bipyramidal with the 5 s pairs, right? With this one, so you have 1, 2, 3, 4, 5, 6, 6 sigma bonds, and 1, 2, 3, 4, 5, 5 sigma bonds, 5 sigma bonds and 1 lone pair coming from the octahedral electron pair geometry, right? One lone pair is there, so it is going to be, right, square pyramidal, no? So those are the shapes. See, such kind of whether such kind of answer is appearing. Trigonal planar, trigonal pyramidal, trigonal bipyramidal, square pyramidal. Yes, answer number 5. So your answer is answer number 5. Right? Okay, that is for the question number 21. Right? Quickly go towards question number 22. If you have any questions, just copy the chat box, right? Right. Let's copy the question number 22. Question number 22. Question number 22 is regarding some covalent molecule which is a dipole moment. Right? Dipole moment. So this is regarding polarity of molecules. Polarity of molecules. See? Right, let's discuss about that topic. I think we have such a topic at the topic number 16. Let's quickly discuss about the polarity of molecules, and then we can approach the question, right? Okay, so at the page number 16, right, of your short notes set, right, at the page number 16, you have the short note for the polarity of molecules, right? Let's quickly discuss the things appearing, the major stuff appearing with that topic, right, and then we'll approach the question, right? What are things you should know? Right, before coming up with the polarity of molecules, first we can discuss about the polarity of bonds. Let's first discuss about the polarity of bonds, polarity of covalent bonds. After that, we can study the thing about the molecules. Right? First, the polarity of covalent bonds. Right? The idea is this. Right? So, if you are with a covalent bond, where the two atoms connecting to each other are with different values for electronegativities. So, like HCl, when two atoms are like this with two different values for the electronegativities, right, what will happen? The two electrons are not at the center now. The two electrons are not at the center. The two electrons will attract heavily towards more electronegative atom, not at the center. So, at the atom with great electronegativity, you have some more electron density, so that we say some more slightly greater negative charge is there. More electron density means slightly greater negative charge is there at the corner of the most electron atom. So that can be denoted by a negative delta, slightly higher negative charge. But at this side, as this guy is losing partially of its electron towards the chlorine, here it creates a slightly positive charge, positive delta. Right? So this kind of a bond with these positive and negative poles, this kind of covalent bond with these positive and negative poles are referred to as a polar covalent bond. Polar covalent bond. Polar covalent bond. Right? So polar covalent bonds are made when the covalent bonds are formed by atoms with different affinities. Two poles will create where the negative poles comes up with the higher affinity atom and the positive pole comes up with the lower affinity atom. Right? This polarity of these bonds will be denoted by a parameter called as dipole moment. The polarity of these things, these polar covalent bonds, will be discussed by a parameter called dipole moment, which is a vector. Dipole moment is considered as a vector. Vector means it is a property with a magnitude as well as a direction. Right? So the direction of the dipole moment is actually symbolized by this kind of arrow. Where arrow head is towards the negative pole and arrow tail is towards the positive pole. Arrow head is towards the negative pole and arrow tail is towards the positive pole. At the tail, you can clearly see this kind of a positive sign indicating the positive pole. Right? This is how the direction of the dipole moment is indicated for polar covalent bonds. Clear? And the magnitude of the dipole moment is given by this equation. Dipole moment is mu. Its magnitude is given as from this equation. Delta R, where delta is the partial charge appearing on an atom and R is the distance between the two nuclei, the internuclear distance or the bond distance. R is the bond distance or the internuclear distance between the two atoms, and delta is the partial charge appearing on one of the atoms. That will give you the magnitude of the dipole moment. Right? This is what referred to as a dipole moment of a covalent bond. Dipole moment of a covalent bond. Right? Okay. Right. So sometimes covalent bonds are made from two atoms which are with same affinity values. 2.5, 2.5. So that the two electrons are appearing at the exact center then, not going towards any of the atoms. Exactly at the center of the bond, at the center of the two nuclei, bond distance, right? The two electrons are appearing. So that no poles will be created. No positive pole, no negative pole will be created there. So that such a covalent bond without poles, like this are referred to as non-polar covalent bond. Non-polar covalent bonds. Non-polar covalent bonds. Non-polar covalent bonds. And these are always referred to as 100% covalent bonds. 100% covalent bonds. Right? When it comes to these things, these covalent bonds are not 100% covalent, because when it comes to these bonds, the two atoms are attracted not via only the covalent character, not via only the sharing electron character, that is the covalent character, but also via the opposite charge attractions of the opposite charges. The two atoms are connected to each other not only via the sharing pair of electrons, but also via the attractions of two opposite charges, the ionic character. So some ionic character is also there with this bond to combine the two atoms, covalent character as well as ionic character. So that these are not referred to as 100% covalent situation. These are polar covalent bonds with some ionic character. In these cases, the two atoms are connected only via the sharing pair of electrons, only due to that. So that is 100% covalent nature, right? This is how, right? We have studied about the right polarity of a single covalent bond, right? Okay, so those two things are there with the note at the two first boxes, right? Polar and non-polar covalent bonds, right? You clearly see the stuff and you can go through the things appearing there, right? Then at the third box, they had discussed about the second box, dipole moment thing. So dipole moment can be denoted like this, and its magnitude will be given like this, right? Those things are also indicated at the box number 2, right? And some calculation also given at the box number 2 to calculate the percentage ionic character of a covalent bond. To calculate the percentage ionic character of covalent bond, some calculation also given at the box number 2, right? Okay, so let's discuss a bit about that thing as well, right? Let's cover up that theory as well. How to calculate the percentage covalent character or percentage ionic character of this bond, right? So dipole moment data can be used to calculate the percentage ionic character of this bond. Some ionic nature is also there with this bond, no? Right? Let's see how to calculate the percentage ionic character of this kind of bond. Only in 2020 paper, this question was asked, right? After that, still yet to come a question from this section, calculating the percentage ionic character or calculating the percentage covalent character of a covalent bond, right? Okay, let's discuss how to calculate the percentage ionic character of this bond. Some ionic is also there. How to use the right use these data, dipole moment data, to calculate the percentage ionic character. Right? The idea is this. For that, first of all, you should know some of the data. So you should know, to calculate the percentage ionic character of a covalent bond, right? You should know some practical data. For these kind of questions, some practical data should be given, right? Let's say for the HCl bond, some practical data about dipole moment and the bond distance are given. Let's say those values are given, right? So in this question, it is said, right? So the bond distance is given as 127 picometers, and dipole moment is given as 3.45 into 10 to the power minus 30, no? 3.45 into 10 to the power minus 30 coulomb meters. Delta is given in coulombs, charge unit, r distance is given in meters, coulomb meters, dipole moments unit, right? Okay, let's say these two things are also given. Then how to come up with the percentage ionic character? So I am doing the calculating the percentage ionic character of HCl bond, right? Okay, let's do the calculation, right? So actually percentage ionic character means there is the equation of that. Percentage ionic character means the actual charge on an atom divided by the charge on an atom if bond is 100% ionic into 100. This is the equation they use to calculate the percentage ionic character. Right? Actual charge on an atom means this charge, the delta charge. It is the actual charge on an atom because of the electronic movement towards the higher affinity atom. So actual charge means the actual delta value. Delta value divided by charge on an atom if the bond is 100% ionic. If the bond is 100% ionic means if bond looks like H plus and Cl minus. If the bond is as H plus and Cl minus, that is a 100% ionic situation. If that kind of thing appears, the charge on an atom is at the bottom and the delta charge at the top into 100% will give you the percentage ionic character. Right? This is how it is to calculate. Let's calculate the stuff. Right? So actual charge on an atom, first thing. Calculating actual charge on an atom. Right? Actual charge on an atom. That is delta. That is equal to, delta is equal to mu over r. Dipole moment, practical data divided by r. Right? This gives you dipole moment is 3.45 into the power minus 30 coulomb per meter. R is actually 127 picometers. 127 picometers. Pico means 10 to the power minus 12 meters. So this value will be given as 2.27 into 10 to the power minus 20 coulombs. That is the actual charge on an atom. Right? Then charge if the HCl is 100% ionic. HCl is 100% ionic. That means HCl looks like this. H plus and Cl minus. 100% ionic means that no? HCl looks like this. Then charge on an atom is what? Then charge on an atom plus 1 and minus 1. So charge on an atom is equal to the electronic charge. Plus 1 or minus 1. Plus 1 again. Relative charge. 1 of electronic charge. The charge of this thing. 1 of electronic charge, right? 1 electron is great. You have more number of electrons, 1 electron than the protons there, right? So the charge is 1 electron charge. Yes, you have less 1 of electrons than the positive charges. So 1 electron charge is in excess here, less in here. So charge is that. So 1 electronic charge means 1 into, right, 1.602 into 10 to the power minus 19 coulombs. Right? So that is the charge. This is number 1. This is number 2. If you apply these two things here and here and multiply by 100, you get the ionic character. You get the percentage ionic character. Right? So I'll write it here. So, right? So your percentage ionic character equals, right? This is the actual charge appearing 2.27 into 10 to the power minus 20. And the charge if the bond is 100% ionic is 1.602 into 10 to the power minus 19 into 100. So simplification of this thing will give you 17%. right? So this is the percentage ionic character. So when it comes to HCl, the bond is 17% ionic and 83% covalent. The bond of HCl is 17% ionic and 83% covalent. Rest is covalent, right? This is the idea. So we have a problem, I think. Let's discuss about that thing. So just go to the thing. Actually, that thing is there in your note. Let's go to the note. See what they're asking. So can you please explain how to get the charge if HCl is 100% ionic? Okay. So it's charged, no? Right? It's like this. So if the HCl is 100% ionic, that means no covalent. HCl is 100% ionic, that means no covalent part there. That means HCl looks like this. If the HCl molecule is 100% ionic, HCl would appear like this. No covalent character, no covalent bond, no bond indicating the sharing pair of electrons, no bond there. So the bond is totally ionic, like NaCl, Na plus and Cl minus. So if the bond of HCl is 100% ionic, it looks like this, H plus and Cl minus, not like this, not like this, not like you are having a bond between this, right? So if the HCl is 100% ionic, the thing is like this. So it's charge. So charge on an atom, if bond is 100% ionic, is actually +1 and -1. These plus and minuses are relative charges. If you are coming up with the terminology given in your resource book, these +1 and -1 are relative charges. +1, -1, relative charge. So what is the actual charge? If the relative charge is 1, what is the actual charge? It is 1 into the electronic charge. The actual charge is 1 into electronic charge. This +1 and -1 are the relative charges. 1 unit of charge, minus and plus. So the actual charge in coulombs is 1 into the electronic charge. For the sulfate, SO4 2 minus, the 2 minus is the relative charge. What is the actual charge? Actual charge means the charge indicated in coulombs. So the actual charge of sulfate ion is 2 into the electronic charge, 2 into 1.602 into 10 to the power minus 19 coulombs. That is the actual charge of sulfate ion. Right? That is how this thing appears. If you need a simplification, if you need further more simplification, it looks like this. So Cl minus means you have 17 protons and 18 electrons there. I'm just simplifying the stuff. The idea. Cl minus means you have 17 protons and 18 electrons. That is why the minus charge appears. 17 protons means what is the total charge there? 17 into the smallest charge, 1.60, that thing, 17 into. That is the positive nature, positive charge. And 18 electrons, 18 into 1 point that thing as negative charges. So the net charge would appear as, for 17 protons, 17 electrons will cancel off. So net charge will be appearing as from 1 electron. So 1 electronic charge is the net charge. So that is how the charge on Cl minus is considered. The charge on the H plus is the opposite of that. This charge with minus here, with positive here. Is it okay? Right now? Right, okay. Right, හරි. එහෙනම් අපි වැඩි ඉස්සරහට යමු. There is some theory part which had been asked in 2020 question paper, the structured paper. but not after that. ඒක නිසා ඒක අහන්න පුළුවන් ඉස්සරහට පොඩ්ඩක් පරිස්සමෙන් බලන් ඉන්න. right එතකොට මේ ඔය තමයි part එක. Then let's discuss about the polarity of molecules quickly. Polarity of molecules is very important discussion, right? We up to now we have just discussed only the polarity of bonds, only the polarity of covalent bonds. That is what we have discussed up to now. Let's quickly discuss about the polarity of molecules, right? Polarity of molecules, right? See, polarity of molecules. So we have two types of molecules. We have two types of chemical species: polar species and non-polar species. Two types of chemical species, right? Polar species as well as non-polar species. Polar species. What is the definition? Polar chemical species. Polar molecules or polar ions or anyway polar species. Right? So polar species are the species with a net dipole moment. A chemical species that means it could be an ion or a molecule with, right, I'll write it here. For a species, a chemical species, it could be an ion or a molecule with a net dipole moment. I'll write dp, dipole moment, not equal to 0. With a net dipole moment not equal to 0. What are non-polar species? Non-polar species. Non-polar species are the chemical species. A chemical species could be an ion or a molecule with a net dipole moment equals to 0. Equals to 0. Right? Okay, in these cases, we had discussed about a new term referred to as net dipole moment. What this means? Net dipole moment. What this means? Here the net dipole moment is not equal to 0. Here the net dipole moment is equal to 0. What this thing means? That is next discussion. What is this net dipole moment thing means? So we know about the dipole moment, right? We know about the dipole moment of a bond. And what is this net dipole moment? The net dipole moment is the vector summation, vector addition of all the dipole moments of your molecule, of your species, chemical species. Right? The vector summation, net dipole moment means vector addition of all the dipole moments of bonds in the chemical species. I'll tell you what that is with some example. See, let's discuss about NH3. Let's discuss about NH3. NH3. Some H2O. Let's see how to come up with the net dipole moment. CO2. Right? BCl3, CCl4 or CH4. See how to come up with the net dipole moment and the stuff. Right? So, first of all, to decide whether a molecule or species is polar or non-polar, first of all, what we should do is, actually, first of all, you have to draw the chemical species with the correct shape. You have to first draw the naturally existing chemical species, the chemical species existing in nature. You have to come up with that. That means you have to draw the structure with the correct shape. That is the first thing to do. Yes, I have drawn those. Then you have to mark the dipole moments of each and every bond. You have to mark the dipole moments of each and every bond. This is how we have to decide a structure is polar or not. Mark the dipole moments of each and every bond. So for the NH bond, the electrons are going towards nitrogen. So nitrogen is a negative pole, hydrogen is a positive pole. So that you can mark the dipole moment like this. Right? For this NH bond, nitrogen is a negative pole, hydrogen is a positive pole. As the electrons are going towards nitrogen, so dipole moment should be marked like this. It's a vector. Direction is very important. In this case, for this bond, nitrogen is negative, hydrogen is positive as the electricity of nitrogen is greater. So dipole moment could be marked like this. Those are all the dipole moments of these bonds. Then what we need is, these are the dipole moments of the bonds. And what we are referring is the net dipole moment. What is net dipole moment? Vector addition of all the dipole moments of bonds in the chemical species. So the vector addition of these three vectors are referred to as a net dipole moment of this NH3. These are the dipole moments of individual NH bonds. The net dipole moment is the vector addition of these three. So vector addition. So you have to consider the horizontal part as well as the vertical parts. So you have to resolve this thing vertically and horizontally. Take the resolves. And you will see ultimately when it comes to resolves, right? The horizontal parts will cancel off. If you are with a molecule like this, the NH3 like this, NH3 looks like this, no? Molecule looks like this, no? So your vertical parts will be like this towards up, but horizontal part will be like this. Horizontal parts, right, will form a vector with three components, right, where you connect to one single point. Horizontal parts, right? So those will cancel off. Horizontal parts එක ළමයි එන්නේ මෙහෙම. Horizontal parts එක එන්නේ වාගේ. හරි vectors තුනක් එයි මෙහෙම. Horizontal parts තුන. cancel off වෙනවා. Vertical parts එක මෙහෙම. ඕම එනවා උඩට. හරි. ඒකට ඊට උඩට ඉතුරු වෙනවා. ඒකට වාගේ මේකේ net dipole moment is going to be something like this. උඩට ඉතුරු වෙනවා. හරි. මෙහෙම උඩට ඉතුරු වෙනවා. So this means in NH3, this is your negative pole and this is your positive pole. In NH3, you have two poles, positive and negative poles. So NH3 is considered as a polar molecule, polar species, as you are with a net dipole moment. Polar species. As mu is not equal to 0, it's a polar molecule. What about this? See, first mark all the dipole moments of individual bonds after drawing the structure with the correct shape. Then mark the net dipole moment the horizontal parts will cancel off. The horizontal parts will cancel off, but vertical parts will remain, will add together to give you some net vector resolve. After resolving, you get some net vector like this, where the positive thing is at the center of two hydrogens and the negative thing at the arrowhead is at the oxygen. So arrowhead denoting the negative pole, this positive thing denoting the positive pole. So H2O is a polar molecule as net dipole moment is not equal to 0. Right? What about carbon monoxide? See, first draw the structure with the correct shape, then mark all the dipole moments available with bonds. So CO bond, the electrons are going towards oxygen, which is more electric than carbon. So the dipole moment will be like this. For this thing, it is also like this. Carbon carrying the positive pole, oxygen carrying the negative pole. So vector addition is going to be 0. So two vectors appear like this, towards here and towards here. Two vectors appear like this. Opposite vectors with same magnitude. Opposite vectors with same magnitude. So the resultant vector is 0. Resultant vector is 0. Equal to 0. Resultant vector. So normally we note it as mu bar resultant vector. It is equal to 0. That means it is a non-polar species. Here it is a molecule, non-polar molecule. A chemical species with a net dipole moment equals 0. Non-polar species, non-polar molecule in this case. Right? See this one? So chlorines are more introduced. So arrow head towards chlorines like this. After drawing the structure with the correct shape, we mark the dipole moments of each and every bond. So again, you could see some three vectors with 120 angle coming up with same point. So this vector addition is giving you a 0 again. This vector addition will give you a 0 again. It is clear, right? As you can see the results here. So these are the vector results, right? Horizontal and vertical results, right? So if you have to put those things like this, you have to put these values as x. You have to put these values as x. The magnitude. You will see as these bonds are with 60-degree angles, 60-degree angles, because this is 120, 60 degrees each. So towards up it is x sine 60, x sine 60. Towards down again x sine 60. So values will cancel off. X sine 60 upwards, x sine 60 downwards. The results, vertical results will cancel off with these two guys. The horizontal results. So this one will give you, one result will give you x cos 60. Such two are there, x cos 60, two years here, x cos 60. So 2x cos 60. That means 2 into 2x cos 60 is half. Cos 60 is half. That is x. So you have a magnitude of x towards left hand side. So magnitude of x is appearing at towards right hand side as well. So same magnitudes of opposite directions. So those two will also cancel off. So vertical parts as well as the horizontal parts will cancel off with this kind of a vector addition. So this guy net dipole moment is going to be 0. Vector addition is 0. So this is non-polar. It's non-polar. Right now? මේකෙත් එහෙමයිනේ. මේකෙත් ඔයාලට non-polar එකේ පේනවලම හොඳට. අර මේක මෙහෙම ගත්තා නම්. Right? If you have to consider the CH4 stuff like this, CH4 is a kind of tetrahedral molecule. CH4 මෙහෙම දන්න ඕමනි. ටෙට්‍රායිඩල් මොලිකියුල් එකයි. you see ටෙට්‍රායිඩල් වෙනවනේ. ඔන්න ටෙට්‍රායිඩල් ඉන්නවා. මේක මෙහෙම බැලුවට පස්සේ මට පේන්නේ නැහැ අර මේ රිසෝස් ටික කැන්සල් ඔෆ් වෙනවා කියලා. මේක ඔයා මෙන්න මෙහෙම බැලුවොත් if you see this thing like this you can see two V shapes. You can see two V shapes. One V here and another V at this corner. One V here. හරි? මෙහෙම V එකයි මේ අතර V එකයි තියෙනවා. ඒතර මොකද වෙන්නේ? vertical resource ටික cancel off වෙනවා V's දෙකේ. මේ පැත්තට දෙක cancel off වෙනවා. මේ දෙකේ horizontal resource දෙක cancel off වෙනවා. vertical resource දෙක උඩට ඉතුරු වෙනවා මේ දෙකේ. මේ දෙන්නගෙත් vertical resource දෙක horizontal resource දෙක cancel off වෙනවා. vertical resource දෙක පහළට එනවා. So down resolve and this up one, those two will cancel off. Right? එහෙම ඔය CH4 කියන tetrahedral structure එකෙදිත් resource ටික cancel off වෙනවා. Right? That is also coming up with net dipole moment equal to 0. So that is also non-pole. ඔය විදිහට ළමයි හරිද අපි මේකට කියන perfect shapes කියලා. All the perfect shapes are coming up as non-polar species. Perfect shapes. What are perfect shapes? Perfect shapes are the ones where you don't have lone pairs with your central atoms, where you don't have lone pairs with your central atoms, but all the connected stuff are the same. All the connected stuff are the same and no lone pairs with your central atom. Such things are referred to as perfect shapes. CO2, BCl3, CH4, PCl5, PCl5, SF6, some more stuff, PCl5, SF6, right? And cancel off, PCl5. All the connected guys are the same and no lone pairs. SF6, those are referred to as perfect shapes. For all the perfect shapes, the net dipole moment is equal to 0. So that those are non-polar. Alright? The perfect shapes ටික non-polar වෙනවා. Perfect shapes එන්න ඕනේ. හරි? මේක නිකන් BCl3 තමයි. නැත්නම් BCl2F වුණොත් හරියන්නේ නැහැ. BCl2F වුණොත් definitely you have a dipole moment towards this side. So non-polar. Polar becomes polar. Perfect shape එකක් වෙන්න නම් all the connected atoms should be same with no lone pair appearing. Those are perfect shapes. Then your net dipole moment becomes 0 and those are non-polar. එකක් හරි atom එකක් හරි වෙනස් වුණොත් those become polar. Right? ඒ කොහොම තමයි polar non-polar species තෝරගන්නේ by considering net dipole moment. If the net dipole moment is 0, those are non-polar. If you have net dipole moment, those are polar. Right? හරිනේ? අපි බලමු question එකක් අහලා තියෙනවා නේද අපි පැත්තට යමු. Right, no, right. Shit, ne? So molecule එක molecule එක perfect shape යන අනිවාර්යෙන්ම non-polar. Right? Perfect shape නැතුවත් non-polar වෙන්න පුළුවන්. Like this. Perfect shape යන අනිවාර්යෙන් non-polar. හැබැයි perfect shape නැතුව මෙහෙමත් non-polar වෙන්න පුළුවන්. හරි. What you have to consider is just net dipole moment. XCF4 එකක් cancel off වෙනවා. නේ? cancel off වෙනවා. Perfect shapes නම් ආයෙත් ඇඳලා ඉන්න දෙයක් නැහැ. Perfect shapes නම් ඇඳලා ඉන්න දෙයක් නැහැ. අනිවාර්යෙන්ම cancel off වෙනවා. No need to draw if you are dealing with a perfect shape. But if not, just draw the stuff and see. The net dipole moment is equal to 0. Non-polar. Right? හරි ඔය තමයි වාගේ ඒ කාරණා ටිකව දැනගන්න ඕනේ. Right? ඊට පස්සේ අර පොඩ්ඩක් අහලා තියෙන NH3 ගේ polarity එක කොහොමද decide කරන්න කියලා, which is more polar and which is less polar කියන එක concern කරලා තියෙනවා. For that we have to consider the lone pair effect as well. Or we have to consider the lone pair effect as well to consider which one is more polar, the NH3 or NF3 that is written in your note. Just go to that and see. right? Normally a lone pair with a hybrid orbital comes up with a dipole moment, slight dipole moment. That is also should be concerned when deciding the more polar stuff out of NH3 and NF3. NH3 NF3 දෙන්නගේ වැඩියෙන් පෝල එකන decide කරන්නවාට එතකොට dipole moment of the lone pair also should be considered, right? So slight dipole moment will appear with the lone pair as well, so that is also should be considered to concern about which is more polar and which is less polar out of NH3 and NF3 should be known, right? කතාව දැනගන්න ඕන. අර නිකන් දේවල් වලට බලන්නේ ලෝන් පෙයා ඉෆෙක්ට් එක අපි යූස් කරන්නේ නැහැ. දෙන්නෙක් කම්පෙයාර් කරන්න කිව්වම කවුද වැඩි කවුද අඩු කියලා ගන්නකොට ලෝන් පෙයා ඉෆෙක්ට් එක පොඩ්ඩක් කන්සිඩර් කරන්න. හරි ලෝන් පෙයාස් තියෙනෙත් අර හයිබ්‍රිඩ් ඕබිටල්ස් වල නිසා ලෝන් පෙයාස් තියෙනෙත් මේ වගේ හයිබ්‍රිඩ් ඕබිටල්ස් වල නිසා හරි ඔයාට ඒ වල ඩයිපෝල් මොමන්ට් එකක් ක්‍රියේට් වෙනවා. හරි අර මේ පැත්තට ඔයාගේ පොසිටිව් චාර්ජ් එක මෙතන තියෙන්නේ උඩ ලෝබ් එකේ ඩයිපෝල් මොමන්ට් එක මෙහෙම එන්නේ පහළ ලෝබ් එකේ ඩයිපෝල් මොමන්ට් එක මෙහෙම එන්නේ හරි පහළ ලෝබ් එකේ ඩයිපෝල් මොමන්ට් එක මෙහෙම එන්නේ මේ පොසිටිව් චාර්ජ් එක කියන්නේ මේ නියුක්ලියස් එක හරි නියුක්ලියස් එක පොසිටිව් හරි ඒතර ඔය දෙක කැන්සල් ඔෆ් වෙනකොට උඩට පොඩි ඩයිපෝල් මොමන්ට් එක ඉතුරු වෙනවා හරි උඩට ඩයිපෝල් මොමන්ට් එක ඉතුරු වෙනවා. ඔක තමයි ඔය NH3 එකේ මාක් වෙලා තියෙන්නේ. මෙතන කැන්සල් ඔෆ් වෙද්දි උඩට පොඩි ඩයිපෝල් මොමන්ට් එකක් ඉතුරු වෙනවා. ඒක තමයි උඩට මාක් වෙලා තියෙන්නේ when considering NH3 and NF3 which is more polar and which is less polar, right? ඒක කන්සර්න් කරන්න වෙනවා ලෝන් පෙයා ඉෆෙක්ට් එක කන්සර්න් කරන්න වෙනවා ඔය වෙල් කම්පොසිෂන් එකේ. ඒක තමයි නෝට් එකේ මම දැන් ක්ලියර්ලි දාලා තියෙන්නේ, right? හරිනේ. හරි ඉතින් ඔය තමයි ඒ කාරණා ටික dipole moment of molecule, right? හරිනේ. අපි ඔය ටිකත් එක්ක යමුද අපි වැඩි ටක් ගාලා කතා කරමු. question number 22 we have it, right? Right, let's concern the question number 22. Right, question number 22. Right, see what again? M is an element which belongs to second period in the periodic table, right? It forms a covalent molecule MCl3. MCl3 කියලා covalent molecule එකක් හදනවලු. මෙයා second row element එකක් කියලා කියනවා. second period එක කියන්නේ second row element now, right? You can't exceed the octet, right? You can't exceed the octet. Octet is special there, which has a dipole moment. අර මෙයාට dipole moment එකක් තියෙනවලු. හරි molecule එකට තියෙනවා dipole moment එකක් තියෙනවලු. right? Has a dipole moment. ළමයි මොලිකියුල් එක ඩයිපෝල් මොමන්ට් එක කියලා net dipole moment එක. මොලිකියුල් එක ඩයිපෝල් මොමන්ට් එක net dipole moment එක. If you are regarding the dipole moment of one single bond, that is just the dipole moment. But if you are regarding the dipole moment of a molecule, that is a net dipole moment. So has a dipole moment means your net dipole moment is not equal to 0. It's a polar stuff. Right? Has a dipole moment means that net dipole moment is not equal to 0. Dipole moment of a molecule is actually net dipole moment. Dipole moment of a chemical species with more than one single covalent bond is referred to as the net dipole moment. Dipole moment of a species with only one single covalent bond is just a dipole moment, right? Okay. Hard. The group of the periodic table which M belongs to. හරිද? දැන් MCl3 කෙනෙක් කෙනාව බලන්න අඳින්න පුළුවන් various methods මොනවද කියලා. MCl3 it's a covalent molecule without charge. Charge is 0. හරි? අඳින්න පුළුවන් ක්‍රම මොනවද බලන්න. covalent ගයිනෝ MCl3 අඳින්න පුළුවන් මට මෙහෙම. This is one way of drawing MCl3. second row නේ. තොර නිකන් අර උදාහරණයක් ගත්තොත් BCl3 වගේ. boron chloride වගේ. right? MgL3. නැත්තම් ඔයාලට මෙයා අඳින්න පුළුවන්. මේම. ඔය ක්‍රම දෙක විතරයි තියෙන්නේ. example එකක් ගත්තොත් මේක like BCl3 මේක නිකන් NCl3 වගේ. අර second row නේ වෙන්න ඕනේ. second row කෙනෙක් වෙලා Cl. ඔය ක්‍රම දෙක විතරයි තියෙන්නේ. වෙන විදියක් නැහැ. හරිද? second row elements එක without charge නේ. without charge කියන එක bond එකෙන් set වෙන්න ඕනේ. හරි එතකොට මේක ගත්තොත් මේ dead diamond moment එක 0. it's a perfect shape. dead diamond moment is always equal to 0. that is non-polar. මේක perfect shape එකක් නෙමෙයි. you have dead diamond moment, right? then CL ගත්තොත් dead diamond moment is there. mu bar is not equal to 0. polar. polar molecule. So the answer should be this one. Answer should be this one. Has a dipole moment. So answer should be this one. So its group number, that is what they are asking, no? The group of the period. What is the group number? As this one is without a charge, right? Number of electrons around it at the valence shell gives you the group number. Ne, harne? At the valence shell, if you have it 1 electron, it is group 1. At the valence shell, if you have it 2 electrons, it is group 2. At the valence shell, you have it 3 electrons with a neutral atom, right? Group 13. At the valence shell, if you have it 4 electrons as a neutral atom, you have group 14. 4A කියන එකනේ, group 14. As a neutral atom, if you have it 5 electrons at the valence shell, it is group 5A, group 15, like that, no? So this guy's group number is with, as this guy is with 1, 2, 3, 4, 5, 5 electrons at the valence shell. Shell as a neutral atom. So group number is actually group 5A. 5A. This is the UK notation, and the US notation it is group 15. 10 එක තුල ගන්න වෙන්නේ P block එක group 15. So the answer is answer number 4. So the answer is answer number 4. Group 15. Right? Hot. That is the question number 22. Right? Okay, let's come up with the next question. The question number 23 and 24. Those are regarding the ionic bond. Right? Regarding the ionic bond. (23 and 24). Right? Regarding ionic bond, I'll write it. Right? So what are the things we should know regarding the ionic bond? First, we'll discuss about the ionic bond. The theory you should know about the ionic bonds. Right? We need to discuss the ionic bonds ගැන මම දැනගෙන ඉන්න ඕනේ කියලා. Right? So ionic bond is the electrostatic attraction, right? Between the cation and anion, right? So electrostatic attraction between a cation and an anion is electrostatic attraction. Is referred to as the ionic bond. Right? This electrostatic attraction is referred to as the ionic bond. Right? ඔය තමයි ionic bond එක කියලා කියන්නේ. Right? තවම දැනගෙන ඉන්න ඕනේ. So the strength of the ionic bond will be decided by the polarizing power of the cation and the polarizability of the anion. The strength of the ionic bond as well as the covalent character arises at the ionic bond will be decided by the polarizing power and the polarizability polarizing power of the cation and the polarizability of the anion. Let's discuss the concept there. Right? That is referred to as the Fajan rule, which discuss the origin of covalent character of an ionic bond. Right? Of an ionic bond. Right? Let's discuss. Right? So what happens? Lamai, even though the electron cloud of the cation is highly attracted to its nucleus, even though the electron cloud of the cation is highly attracted to its nucleus, why is that? Because it is a positive charge. That positive charge will greatly attract the electron cloud towards the center, right? And it's a smaller size, so that the valence shell is very close to the nucleus, so that electron density will be greatly attracted towards the nucleus, right, of the cation. So even though the electron cloud of the cation is greatly attracted towards its nucleus, when it comes to anion, its electron density or the electron cloud, basically the valence electrons, the outermost electrons are not that much attracted to its nucleus. When it comes to anion, its electron density is not that much attracted to its center nucleus. Why is that? Because the anions are situated, basically valence shell electrons, the outermost electrons are situated bit away from the nucleus when it comes to anion, not like in cation. And the other thing is, now with the anions you have more electrons, you have more negative charges compared to the positive charges at the nucleus. So anions are with some bit powerful nature when it comes to anions, so not that much keen towards attracting the nucleus when it comes to anion. So that what will happen because of that? Because of that, anion will respond. Anions, the electrons of the electrons of your anions will respond to outer charges. Because of that, electrons of your anion respond to outer charges, as those are not that much attracting towards its own nucleus. Those will respond to electrons of the anion will respond to outer charges, right? So that this becomes like this. So that as electrons of the anions responds to outer charges, basically to the charge of the cation, as the electrons of the anion responds to that, these electrons will attract towards cation and ultimately obtain some force. The electron density will attract heavily towards cation and ultimately get some great electron density at this corner and some less electron density at this corner. So it will get polarized. More electron density at this center, this corner means negative charge, negative delta, some more electron density, some more negative density, this is positive delta. So anions get polarized like this because of the electrons, the behavior of the electrons of the anion, right? Because of this, some covalent nature appears with the ionic bond. Some covalent nature appears with the ionic bond, right? What is covalent nature? Covalent nature means sharing a pair of electrons, sharing electron densities. Sharing electron densities, that is referred to as the covalent nature. Ionic nature is what? Ionic nature is attraction via opposite charges. Attraction via opposite charges. That is ionic nature. Covalent nature is sharing electron densities. So in this case, with this polarization, this anion tends to share some electron density with the cation. Share කරන්න උත්සාහ කරන බවක් නෙවෙයි. These guys tend to sharing some electron density. Share කරන්නේ මේ දෙන්න අතර space එකට electrons එවනවා. Anion will give some electron density towards the space in between the cation and the anion, trying to share some electron density. That is what happens. That is referred to as a covalent nature. So some covalent nature appears with the ionic bond due to this arising of poles of your anion. Right? This is what we refer to as polarization of the ionic bond, so that covalent character will arise. Right? So this thing will heavy when you are with some greater charge. When you are with some greater charge with your cation and some smaller radius with your cation. If your cation is with a greater charge and smaller radius, this guy's charge strength density, this charge strength is high. So that will tend to greatly attract the electron density of the anion. So that when this thing is greater, we say the cation's polarizability. Sorry, polarization power of the cation is high. That means cation's ability to attract the electron density towards itself. Cation's ability to attract the anion electrons towards itself is referred to as its polarization power, that is high when it is with a greater charge density, with greater charge as well as small radius, greater charge strength. Right? When it comes to anion, if it is with a greater negative charge as well as greater radius, greater size, its electron density will greatly attract towards the cation. With a heavy charge means more electron density is there, so easily will get attracted to the positive charge. And greater radius means its valence shell electrons are far away from its nucleus, anion's nucleus, so that it's keen to respond to outer charges. Right? Those things will happen when these situations are met. So anion's polarizability, ability to arise poles from its own electron cloud, is high when these things appear. So when these two things happens, polarization of the covalent bond is high, so that the covalent character of your ionic bond increases. When the covalent character increases, your ionic character decreases. Ionic character decreases. අරනම 100% වෙන්නේ covalent ionic දෙක එකතුවනේ. bond එක 100% nature එකේ ඉන්නේ covalent ionic දෙක එකතුව. හරි? covalent nature එක වැඩි වෙනවා කියලා කියන්නේ ionic nature එක අඩු වෙන්න ඕනේ. The total is 100 නේ. 100% නේ. covalent nature එක වැඩි වෙනවා කියලා කියන්නේ ionic nature එක අඩු වෙනවා. summation එක 100% වෙන්නේ. Right? හරිනේ? ඔය idea එක නේ. So එහෙනම් covalent character decreases means ionic character decreases. Right? So when the ionic character decreases, normally what happens? The ionic bond strength decreases. As ionic bond strength decreases, the melting points of ionic compounds decrease. Ionic character එක අඩු වෙනකොට ionic bond strength එක අඩු වෙනවා. Ionic bond strength එක ionic character අඩු වෙනවා. Ionic bond means the ionic character, the charge character, and ඒක අඩු වෙද්දී ඔයාගේ ionic bond strength එක අඩු වෙනවා. ඒ කියන්නේ it is easy to put the particles apart by applying a less amount of heat as well. That is what we are referring to as the melting points and boiling points. No? Boiling point at the melting points and boiling points, what happens is actually the coarsely packed particles, right, will get apart from each other. That is what melting is. That is what boiling is. Melting means a solid convert into liquid. No? There what happens? In a solid, the particles are very close to each other. When it becoming a liquid, the particles will get apart from each other. So in melting, what happens is particles are going apart from each other. So if the bond between that thing, those two particles are weaker, it is easy to put them apart. Melting is easy when the bond is weak. So melting is hard when the bond is strong. So melting points are greater when the bond is strong. Melting points are weaker when the bond is weak. So that when the ionic bond weakening like this, ionic gravity decreases means ionic bond weakening, right? So that melting points of ionic compounds decrease with this effect, right? That is the most important stuff here, right? This is all about the polarization of the ionic bond, right? Okay, so some more stuff are discussed with this polarization thing in your resource book, right? This is the normal concept, the most important concept, right? And with this, when it comes to polarization power of the cations, some other things are also discussed, right? Basically, this polarization power of the cations will affect the thermal decomposition temperatures of ionic compounds, basically carbonates, hydroxides, nitrates, and those things, right? The thermal decomposition temperatures will be affected by polarization power. That is also discussed in your resource book as well as in our note, right? We'll discuss that thing with the question, right? Okay. හරි ඔය ටික තමයි ඔයා මේක දැනගෙන ඉන්න ඕන කාරණා ටික. So that those are the things what we have discussed with the thing, right? So those things are appearing at the page number 14. 14 වල කතා ටික තියෙනවා. හරි? simplify කරලා තියෙනවා. Right? Go to the note as well. හරි? thermal decomposition temperatures ගැන කතා කරමු question එකත් එක්ක. Quickly, let's come to the two questions there with the ionic bond 23 and 24. Ionic bond එකත් එක්ක questions දෙක කතා කරමු. Right. ළමයි අපිට මේ තියෙන විදිහට බැලුවොත් අපිට මේ හුඟක් වෙලාව අඩු වෙනවා වාට මෙට්ලික් බොන්ඩ් එක ගැන කතා කරන්නයි සෙකන්ඩරි ජෙනරේෂන් එක කතා කරන්නයි අපි ඒකට ඔකට වීඩියෝස් දෙකක් එවනවා සාමාන්‍යයෙන් 1 hour වගේ තමයි මෙට්ලික් බොන්ඩ් එකේ ඩිස්කෂන් එක තියෙන්නේ and some 1 hour so 2 hours වගේ දිනවාට second interactions වලට පොඩ්ඩක් ඒ දෙක go through කරන්න ඒ theory ටික cover කරගන්න. අර short notice given නේ short notice ගිහිල්ලා තියෙනවා. එතකොට ඔයාලට පොඩ්ඩක් ඒ note එක නිකන් වීඩියෝ එක පොඩ්ඩක් අහන් හිටියනම් ඔයාලට ඒ ටික cover වෙනවා right. එතකොට අපිට අපි මේ විදිහට වැඩේ කරනවා ළමයි මොකද මේ section එක මෙතනින් ඉවර කරන්න ඕන නිසා right. තව වැඩිපුර දේවල් අපි තියෙනවා නම් තව හොඳ hard questions වලට යන මොන හරි දෙයක් තිබ්බොත් අපි ඒ ටික papers කරද්දී revise කරද්දී අපි ඒ ගැන discuss කරමු right. notes එක මුලින් complete කරන් යන එක කරන්නේ. එතකොට ඔයගොල්ලන්ට metallic bonding ගැනයි ඊට පස්සේ වාගේ second interaction part එකයි අපි අර විදිහට videos දෙකකින් cover කරගන්නවා time එකත් එක්ක right. හරි එහෙනම් අපි ionic bond එක තව ඉවර කරගමු. එතකොට ඔයාලට ඊටර ටික ඒ videos වලින් complete කරගන්න පුළුවන් right. මේ week එකේ මේ වැඩ ටික ඉවර කරන්න ළමයි හොඳේ. අපේ මේ schedule එකේම ඉන්න. එතකොට ඔයාලට මේ weeks ටික ඉවර වෙද්දි මේ month එක ඉවර වෙද්දි ඔයාලට මේ ඔයාගේ syllabus එකම cover කරගන්න පුළුවන් වෙනවා මේ schedule එකේ හිටියොත්. හරි ඒක නිසා අර වැඩිපුර cover කරන්න පොඩ්ඩක් අමාරු වෙන තැන් වලට අපි video එකක් දෙන්නවා. පොඩි videos ටිකක් දෙන්නේ පැය 3ක් විතර වැඩි වුණොත් ඒ ටික cover කරගන්න මේ විදිහට right. එතකොට එහෙම කරාම අපිට මේ schedule එකේ ඉන්න පුළුවන් right. මොකද අපිට ඊළඟ සතිය අපිට මේ cover කරන්න වෙන එකක් නැහැ. මොකද ඊළඟ සතිය අපි තනිකරම chemical calculations වල තමයි focus කරන්නේ. එතන questions ටික හදන එක තමයි අපි next week එකේ තනිකරම කරන්නේ. after මේ Wednesday afternoon session එකේදී right. Wednesday night session එකේදී අපි කරන්නේ chemical calculations questions study කරන එක. අපි මෙතනින් අද දවසින් අපි ඉවර කරනවා අපේ first two units වල discussion එක right. ඊටු ටික videos දෙකකින් පොඩ්ඩක් cover කරගන්න right. කොහොමත් ওই දේවල් ආයෙත් කතා වෙනවා paper discussions යද්දී last 2 months වල right. okay හරි. එතකොට මේ අපි පොඩ්ඩක් questions දෙක අපි කතා කරමු 23 and 24 questions right. ionic bond එක ගැන තමයි කතා කරලා තියෙන්නේ. so 23 question number 23 quickly go through this right. so what they are saying, the increasing order of covalent character of chemical species NaCl, Na2s, right, Kf and what is that? KCl, no? KCl. ඔන්න හොඳ ටැක් ඉන්නවා මේක අහනවාද increasing order of covalent character. covalent character එක අහන්න. හරි increasing order එක අහන්නේ ඉතින් අපි increasing order එක අහලා දින්න කොහොමද? දාන්න right. increasing order තමයි question එකේ අහලා තියෙන්නේ. covalent character increasing order. බලමු කොහොමද වැඩි කරන්නේ කියලා. So when we are with a greater polarization power as well as greater polarizability, if you are with a greater polarization power with your cation and greater polarizability with your anion, your covalent character will increase. That is the idea, no? Right? That is the idea. So polarization power increases when you have a greater positive charge as well as smaller radius. Polarization power will increase with your cation when you have with a greater positive charge as well as smaller radius with your cation. Polarizability of your anion will increase when you are with a greater negative charge as well as with a greater radius size for your anion. Polarizability will increase. When those two things happen, your covalent character will increase. That is the idea, right? Okay, let's consider. First, let's consider these two guys. Where you are with same cation, right? When considering these two guys, same cation is there. So let's consider anion. Cl minus and S2 minus. Cl minus and S2 minus. So it comes Cl minus and S2 minus, right? Cl minus and S2 minus. Cl minus is small and S2 minus is large, as those two guys are isoelectronic species. Those are isoelectronic species, right? So I'm considering these two guys, right? As the cation is same, we are considering the anion. These are isoelectronic species, 18 neutron systems. So with isoelectronic series, greater the positive nature, smaller you are, right? Okay, these are the size. So when it comes to polarizability, when the size is larger, when the negative charge is larger, polarizability is high. So when it comes to polarizability, compared to Cl minus, S2 minus is the greater polarizability, right? So that covalent character for NaCl is smaller than Na2S. Greater the polarizability, greater the covalent character. That is about those two. What about these two? With these two as well, the cation is same, so we have to consider the anion. F minus and Cl minus. F minus is with 10 electrons. Cl minus is with 18 electrons. So species is 18 electrons is always larger than species with 10 electrons. 2 electronic shells and 3 electronic shells. So that the polarizability of F minus is smaller than that of Cl minus. The size matters. Even though the charge of the anion is same, the size of this thing is greater, so that polarizability is great. So that covalent character with these two guys, the Kf is smaller than KCl. Greater the polarizability, greater the covalent character. Right? So I'll let it Kf is greater than, sorry, smaller than KCl. Right? Okay, the things are okay. Now we have to consider these two guys. Right? So we have to connect the guys. How to connect? So connection can be done with the use of these two guys normally. Why? Because these two guys are with a common species. So we can connect the guys, these two pairs. We can connect the two pairs by the common species. Cl is common, right? So it comes to NaCl and KCl. The Cl is common, right? When it comes to NaCl and KCl, I'll write it here, right? NaCl and KCl. Right? So cation is large with KCl compared to NaCl. So the polarizability, so polarizing power is greater with Na plus than the K plus as size is smaller, charge is same. So the covalent character with those two varies as NaCl is with a greater covalent character than KCl, greater the polarizing power, greater the covalent character, right? So that it says NaCl is large, NaCl is large, this guy is large, this guy is larger than this guy, the covalent character. Now we can connect. So that out of these two, this is the largest, but that guy is smaller than the smallest of these couple. Out of these two, the KCl is the largest, but that largest one out of these two is smaller than the smallest of these couple. Right? So the covalent character varies like right? You have with KF and KCl, and then you have NaCl and then Na2S. Right? So such a relationship is there with the answer number 3. So your answer is answer number 3. So answer is answer number 3. Right, no? That is the question number 23. Right. Quickly go to the 24 as well. 24th අපි කම්ප්ලීට් කරමු. right. එතකොට අපේ section එක ඉවරයි නේද? right. Is clear? ඒ approach කරන හැටි බලන්න හොඳේ. දෙන්න තෝරගත්තා. සමාන කට්ටිය දියාගෙන. ඊට පස්සේ ඒ දෙක කනෙක්ට් කරගන්න. ඒකෙත් common එක කරන තෝරගත්තා. right. Next stuff 24. Question number 24. See what it says. When the compounds given below are heated, they decompose according to the reaction. Right? Decompose according to reaction. Right? Okay. This is the reaction. MCO3 giving you MO solid plus CO2 gas. Right? They are asking identify the compound with the lowest decomposition temperature. Right? This is like this now. You have the M2 plus cation here, M2 plus and CO3 2 minus, right? CO3 2 minus anion here. Right? This is kind of a resonance hybrid, no? You are dealing with a resonance hybrid here, right? Carbonate ion appears as a resonance hybrid, right? And ultimately, they are saying you have to form this kind of stuff. M2 plus cation with the O2 minus anion and some Cu2 to release. So these two products to form from these starting compounds, starting ions, what should happen? The heat, the temperature you supply should absorb to this bond should absorb to this bond, and this bond should break by giving all the electrons towards here to form the O2 minus. To form the O2 minus, this bond should break by giving all these electrons to here, to on top of the oxygen, to form the O2 minus. Right? This thing would be easy. This thing would be easy to do if all the electrons are to get attracted to oxygen. If all the electrons are to get attracted to oxygen like this, if the things are attracting towards oxygen like this, then it is very easy to form this O2 minus by breaking the bond from here to form the CO2 and the O2 minus. It's very easy if all the electrons, these electrons are going to be attracted to here towards oxygen, right? No need to consider these things. If you consider this, no worries, right? But if all the electrons are to get attracted to oxygen, it is very easy to break this bond like this, right? And form the O2 minus and CO2, right? Okay. So that process would be easy if your cation here is attracting the electron density towards itself. If your cation here is attracting the electron density of the anion towards itself, this process would be easy. If your cation here is going to attract the electron density of the anion towards left, right, towards the cation, then it is very, very easy to break this bond by attracting all the electrons towards oxygen, as electrons are coming towards here, right? So that can be done easily if you are with a greater polarizing power here, greater polarizing power with your cation. Polarizing power is actually Q plus OR plus the charge density. If you are with a greater charge density with your cation, it is easy to break this bond. Even a little amount of heat would be sufficient, right? If the polarizing power Q plus OR plus, which is referred as polarizing power of a cation, is high, less heat would be sufficient to break this bond, because all the electrons are attracting towards the cation easily, so that with a very less amount of heat, still you can break this bond, as all the electrons are attracted towards the oxygen because of the polarizing power of the cation, if that is high. So the heat needed, or the decomposition temperature, or decomposition temperature needed is less if the polarizing power is high. Very less amount of heat would be sufficient to break this bond, as all the work is done by the polarizing power of the cation, right? On the other hand, if the polarizing power of the cation is less, heat needed is high. The opposite, right? Anyway, polarizing power of the cation and the decomposition temperature, the two guys are carrying kind of inverse relationship, right? So what they're asking is identify the compound with the lowest decomposition temperature. Lowest decomposition temperature comes up with the species with greatest polarizing power. Lowest decomposition temperature comes up with the species with greatest polarizing power. So you have cations, the second row, guys, becomes second row, cations. So you have beryllium 2 plus, magnesium 2 plus, the size increases, calcium 2 plus, like this. What happens going down? Going down, right? Your size of cation increase, so polarizing power of your cations decrease. So going down, decomposition temperatures of carbonates increase, right? Opposite relationship. Going down, decomposition temperatures will increase, right? So what they are asking is the compound with the lowest decomposition temperature. So lowest decomposition temperature comes up with beryllium compound, beryllium carbonate, right? Beryllium carbonate, right? Lowest decomposition temperature comes up with the cation with the greatest polarization power, that is the smallest cation, which is beryllium 2 plus. So beryllium carbonate is with the lowest decomposition temperature. Right now, the answer is answer number 1. The answer is answer number 1. Right now? So that is the answer for question number 24. හරි ළමයි. එහෙනම් අපි අදට මෙතනින් නවතිමු. right අපි ඉතුරු questions එකේ answers ටික මම එවන්නම් ඔයාලට. right ලියලා හරි නැත්නම් වීඩියෝ එකක් විදිහට හරි වන්න. ඕගොල්ලෝ කරන්න ඕන දේ තමයි මෙට්ලික් බොන්ඩින් එකයි secondary interactions වලයි videos ටික මම group එකට දානවා. මේ ටික පොඩ්ඩක් follow කරන්න. right එතකොට අපේ මේ revision එකේ first units වල part එක ඉවර වෙනවා. right okay go through the short notes as well. හරි එහෙනම් අපි අදට නවතිමු. එහෙනම් කට්ටියට good night and see you next week. Goodbye.